Okay, for the last part of kinetics, we'll be looking at the theory for rate of reaction and also reaction mechanism. So under theory for rate of reaction, we will look at the temperature dependence, in which we'll look at Arrhenius equation, and then the significance of activation energy, and then also theories of reaction rate. And then for reaction mechanism, we will look at reaction involving the rate determining step, and also reaction involving several elementary processes. So these are the learning objectives for this last part of kinetics. So you should be able to solve problem associated with Arrhenius equation, explaining collision theory of reaction kinetics, and the third one is solving problem associated with reaction mechanism. So let us look at the effect of temperature on rate of reaction. Okay, so this is based on our observation. So when we raise temperature, we will speed up certain biochemical reactions. For example, cooking of food. So when we increase the temperature, means we increase the speed of the cooking of the food. So the food will cook faster as the temperature increase higher. On the other hand, we slow down reaction by cooling the process using refrigerator or freezing, especially when we want to prevent spoilage of food, for example. Okay, so you put food in the fridge or in the freezer to prolong the shelf life of the food, because we are slowing down the reaction of the microorganism growth. Okay, so the question is, what determine how fast a given reaction will occur? So in 1988, a Swedish chemist named Arrhenius proposed that molecules must possess a certain amount of energy in order to react. So one possible source of this energy comes from kinetic energy of the colliding molecules, and this is where collision theory uh, is introduced. Okay, so according to this Arrhenius theory, if molecules have sufficient kinetic energy, their collision between the molecules can cause bonds to break or even form. So in order to react, colliding molecules must have a total kinetic energy equal to or greater than some minimum value. And this minimum energy required to initiate a chemical reaction is known as activation energy. So the value of activation energy is different from one reaction to another. So the colliding molecule must possess at least an energy of activation energy in order to form product. So if the colliding molecule possess energy lesser than the activation energy, means product will not form. So how does go back to our the earlier question. So how does temperature affect reaction rate? So from the kinetic theory, when we increase the temperature, we will increase the average kinetic energy of the colliding molecules. Means the molecules will collide even more vigorously due to the increase in temperature. So therefore, a greater number of this molecule will have energy of activation energy, or even greater at this higher temperature. So the reaction rate will depend on the energy and the number of collision between the molecules, and it has to um, correctly align, okay, and at the right temperature. And thus, to relate the these factors, Arrhenius equation is introduced, in which the rate constant K is equivalent to A exponent negative EA divided with RT. So A here is referring to the frequency of the collision with correct geometry, correct alignment. Okay. Negative EA here is the activation energy. Okay. So activation energy divided with the temperature and also constant here. So this fraction here is the fraction of molecule with minimum energy for a reaction, and it must be always less than 1, and it has to change along with temperature. So how do we imagine what activation energy is? Okay. For example, you see a lady here playing golf, and there's a small hill here. Okay, so she must um, hit the ball, the golf ball. Okay, putter the ball with sufficient energy in order for the ball to roll over the hill. Okay, so that is called activation energy. Okay, a minimum amount of energy required for direction. Okay, so if the ball does not pass over the hill, then product will not form. In this case, the ball will not roll over into the hole here. Okay. Similarly, when we explain when it comes to chemical reaction, if the energy of the molecule reacting with one another is not sufficient enough, then product will not form. Okay. So when we plot, this is the potential energy versus direction coordinate. So this is the position of the reactant, and this is the activation energy. Okay, this point here. Okay, so the reactant must possess energy equivalent to activation energy or more in order for product to form. So according to Arrhenius, the molecules must acquire a discrete minimum energy before the end products are formed. So therefore, the reactant must pass through an activated state before they can react. So the quantity of energy required by the reactants to overcome this activated state or energy barrier is known as activation energy. So the activation energy for any reaction is the difference between the potential energy of the activated complex and the potential energy of the reactant. Okay, not that potential energy is the y-axis just now. So the Arrhenius equation can be used to calculate the value of activation energy of a given reaction. Secondly, this equation can be used to calculate the rate constant for a given temperature if the activation energy and the A factor is known. So when we log Arrhenius equation, okay, we get this. Ln K equivalent to ln A minus EA over RT. So when we rearrange this log of Arrhenius equation, we get this. Okay, so this is the, if you look, the pattern is y equivalent to mx plus c. So when we plot ln k, y-axis, versus 1 over t, the x-axis, it will give a straight line with the slope of negative EA over r. So this is the slope. Okay. Okay, so negative slope is referring to negative EA over r. Now let us look at example effect of temperature on reaction rate. So the question is asking to determine the activation energy, okay, from Arrhenius equation using this experimental data of formation of nitrogen gas and oxygen gas from the nitrogen oxide gas. So we have this set of data here with its rate constant value. So what we do is we plot. So we plot ln k versus 1 over T, temperature. Okay, the temperature is given, so we convert it to 1 over T. So 1 divided with the temperature, and then the K value given, we convert it to ln. Okay, so we should get a straight line here. Okay, a straight line, and the slope of this straight line indicates the value of negative EA over R. Okay, EA over R according to Arrhenius equation. So the value of the slope is negative 3 times 10 power 4 Kelvin. Okay, because it's a negative slope, so it's negative. Okay, so using the constant for gas, which is 8.3145 times 10 power negative 3 kilojoule per mole, okay, Kelvin per mole. Okay, we get the activation energy of 250 kilojoule per mole. Okay, because both sides are negative here, so we can cross the negative. So that's why we get a positive value of 250 kilojoule per mole. Okay, so the slope here multiply with the gas constant value here, R value, so we get 250 kilojoule per mole for activation energy. Now, if we are given constant K, okay, at two different temperature, okay, we can subtract the value, okay, using these two formula here. So this is referring to temperature 1 and this is referring to temperature 2, so that we can subtract this 2 with 1. Okay, so subtracting will rearrange the formula to become like this here. Okay, ln K2 divide with K1 negative EA over R, because both will have the same value, we put it outside, 1 over T2 minus 1 over T1. So using this formula, if we are given two different temperature, activation energy also can be calculated. Now this is example giving two different constant value at two different temperature. Okay, so this is reaction formation of hydrogen gas and also iodine gas from hydrogen iodide gas. Okay, so at 650 Kelvin, the rate constant value is this. At 700 Kelvin, the red constant value is this. Now substitute these two into the equation. Okay, we can also solve for activation energy. Okay, so the formula is ln K2 over K1. So the K2 value just now, substitute here, K1 substitute here. Okay, K2 is 700 Kelvin, K1 is 650 Kelvin. Just substitute the R value, which is at 0.3145 times 10 power negative 3 kilojoule per Kelvin per mole. We can solve activation energy, which is 182 kilojoule per mole. Okay, not here. Okay, you don't ln separately. Okay, actually the ln should be here. Okay, you divide first and then you ln. Okay, otherwise you get a different value. Okay, next we look at collision theory of reaction kinetics. So the rate of chemical reaction can be affected by these factors here, which are temperature, concentration of reactants, and also catalyst. So according to the collision theory, for two molecules to react, they must collide with proper orientation and sufficient energy to break chemical bonds. For example, we have two molecules here, one molecule here, one atom here. So this is before collision. Okay, so in order to form or break bond, it has to orient the right way. So this green colored atom has to orient the right way in order for the collision to occur and formation and breaking of chemical bond. So this will break, forming this and this. Okay, leaving this behind and forming this. Okay, so if this green colored is orient this way, okay, towards the red colored atom, it won't leads to formation or breaking of new bond. That's why it has to properly orient. Okay, properly oriented, so that reaction will occur. So factors that affect the rate of molecular collision, the orientation of the collision, or the energy of the molecules can affect the rate of a reaction. So the rate of elementary reaction will depend on three factors. The first one is the frequency of collisions between the molecules, or the number of collisions in 1 liter per second. Secondly, the orientation of the molecules during the collision. So it is the fraction of collision with the proper orientation for reaction, and the value is in between 0 to 1. And the third factor is the energy during the collision. So the energy factor represents the fraction of the molecules with the minimum energy required for reaction, and the value is in between 0 to 1. So basically the rate, okay, depends on Z, P, and F. The frequency of the collision, the orientation of the molecules during the collision, and the energy during the collision F. So this is example reaction between iodine gas and also bromine gas to produce iodobromide gas. So suppose there are 4 molecules each of iodine and also bromine. So 1, 2, 3, 4 molecules of iodine, 1, 2, 3, 4 molecules of bromine, okay, in a vessel. So the effect of concentration of the collision between iodine and bromine, so means the total possible collision is 4 times 4, because this first molecule has the possibility to collide with the first one, has the possibility to collide with the second bromine molecule, has the possibility to collide with the third bromine molecule, and has the possibility to collide with the fourth bromine molecule. Similarly, molecule number 2, number 3, and number 4. So if you remember, this is very similar to what you have studied in high school, which is probability, kebarangkalian. Okay, so means if there are 8 molecules each of iodine and bromine, then the likelihood of collision is 8 times 8. Okay, but that is the case if the molecules are 4 each or 8 each. But normally reaction will occur in which the number of molecules is very high. So in general, um, we have reactant A and B produce D. So the chance of collision is equal to Na multiplied with Nb, where this Na and also Nb represent the number of moles of A and B. So at constant volume, the chance of collision of reactant molecules, or the number of collision, is proportional to the product of the concentration um, of the reactants. Okay, so means the rate of formation of D product is equivalent to K times square bracket of A multiplied with square bracket of B. Okay, each represent concentration of A and B. So K here is the rate constant. So let us consider the gas phase reaction between ozone and also nitric oxide. Okay, so we write the rate law expression like this. Okay, with regards to nitric oxide and also ozone. So at standard temperature and pressure and equal, okay, provided we have equal concentration of ozone and also nitric oxide, there are 10 power of 29 ozone nitric oxide collision per cubic centimeter per second. Can you imagine that? Okay, so what actually determine how many of this collision will produce nitrogen dioxide, also oxygen gas? How many? Okay, so basically the collision represent an opportunity for a reaction to occur. Remember, the collision has to align, properly align, in order for the reaction to occur. Okay, so let us consider 3 steps, okay, which involve in the reaction. The first one is approach, followed by interaction, and then lastly separation. Okay, okay, approach of the molecules. So as the molecule approach each other, okay, in which the example just now, nitric oxide and also ozone, okay, the electron clouds tend to repel each other. So the electron clouds of the ozone and also nitric oxide, let me just write back the formula here. Ozone and also nitric oxide to produce oxygen and also the nitrogen dioxide. Okay, so as the molecule approach, okay, the ozone and also nitric oxide, the electron clouds tend to repel each other. Okay, so if the kinetic energy is less than the repulsion force, then no collision cannot occur. Okay, collision cannot occur because the repulsion force is stronger, so it repel. If it repel, then how it's going to approach each other. Okay, so therefore the kinetic energy has to be more than the repulsion force, so that a collision will occur and a possible intermediate can be formed. Okay, okay, so this is the intermediate just now. Okay, so that leads us to the second step, which is interaction. Okay, so the interaction in the between the molecules will form intermediate. Okay, so this intermediate here, okay, the kinetic energy of the colliding molecule is available for redistribution, and bond breaking or bond formation can occur. Okay, so in this case here, um, the bond between the ozone will break. Okay, and the the bond between oxygen and nitric oxide will form here. Okay, so of all of these collision that can occur, only a small fraction are effective and result in chemical change. Okay, and why is that? Remember, in the earlier slide, um, they are 10 power of 29. Okay, ozone nitric oxide collision, okay, per cubic centimeter per second. Okay, so of all of this collision, only a small fraction that are effective and which result in the formation of oxygen and also nitrogen dioxide. And why is that? Remember the term effective orientation, okay, or correct orientation. So the requirement for effective collision, which, okay, in which collision must have sufficient energy for the electron shells to interpenetrate, okay, and the molecule must be in the correct orientation upon collision so that it will leads to a reaction, and the resultant structure will have some stability. So for example, stable bonds or stable species must be formed, which is in this case oxygen and also nitrogen dioxide. So these are the stable species. So the orientation of the colliding molecules is very important because it will determine whether a reaction will occur or not. Okay, so if the nitric oxide and ozone molecules in an orientation that limit rearrangement, then no reaction will occur. Okay, so if it orient like this, then no reaction will occur. Okay, the colliding molecules must be in the correct orientation, then a reaction may occur. So because all three of the requirements must be met for an effective collision to take place, only a small fraction of collision effective in producing a product. So that answers the question just now. So the main feature of a collision theory in bimolecular reactions are the reacting species must come in contact, okay, or collide. Okay, if it collide, it does not necessarily result in reaction. Remember the orientation? Okay, so the colliding species must have greater energy than the activation energy. Okay, so it has to be greater in order for it to form a product, and the species must collide in the proper orientation so that it will lead to reaction. Okay, and of course, the molecules has to be close to each other. Okay, in which kinetic energy must be more than the repulsion forces. So for a bimolecular reaction in which we have reactant A react with reactant B, producing product C and D. So the rate of reaction is equivalent to the number of colliding molecules for per cubic centimeter per second, okay, which is also equivalent to Z. Multiply with fraction effective collision. So we have to consider this, okay, because not all collision leads to effective collision which leads to the production of C and D. So we write the rate law expression as rate equivalent to ZAB exponent E exponent negative E over RT. So Z here is the number of colliding molecules per cubic centimeter per second just now. Okay, so AB is referring to the reactant A and B. Okay, so given ZAB is equivalent to the frequency of collision multiply with the square root of T, okay, multiply with NA and B. So this is the number of mole. Okay, so we write rate law, okay, expression as rate equivalent to K A multiply with B concentration, and this is also equivalent to K and A and B, and A and B is the number of moles. So when we write the rate law here, okay, so we rewrite rate equivalent to ZAB here is equivalent to A square root T and A and B. So we replace this here. Okay, so we replace this here. So that's why we get A T half square root of T exponent negative E over RT here. Okay, so how do we get K here? So when we substitute this here, we bring along NA and B. So NA and B is equivalent to rate divided with K. So that's why we get that expression of K here. Okay, so we get A square root T exponent negative E over RT. Okay, so we learn this formula here. We get ln K ln A plus half ln T minus E over RT, and then we differentiate this, okay, this formula here. Okay, we get this expression here. Okay, and then we rearrange, end up getting d ln K over dt equivalent to E over RT squared. So this is the Arrhenius equation. So if the reaction involves two identical molecules, for example, here A reacting with A producing product, we write the rate law expression like this, okay, or like this, okay, using number of mole, okay, square because 2. So therefore K will be equivalent to Z exponent negative E over RT. So Z is the number of collision, okay, per second. So the theory relates the frequency of factor in the Arrhenius equation with the collision number, which is Z. Okay, so the rate of reaction can be calculated by determining the collision number, which is Z, from viscosity data, and also E, okay, from the reaction rate measurement at two different temperature.